Hi everyone, we are discussing number of zigzag arrays question and we are going to solve it using dynamic programming. So to get started with, we have two pointers, or rather say we have given two numbers left and right noted by L and R here, and our array values can hold our array can hold values in between this range, which is like 1, 2 and 3 are possible values. So just to mention that left and right are inclusive in the range. So there are some rules. The first rule says that adjacent elements cannot be equal, which means that if I place one here, I cannot place another one here at I plus 1 index. Same goes with so basically if this were at index I, so my index I and index I plus 1 cannot have same elements. So this is rule 1. Moving on to rule 2. So now my rule 2 says that no 3 consecutive elements can keep going up. So which means that, see, from 1 we went to 2. So there was an increase. So we basically went up. Now from 2 to 3, we again have an increase in number. So again we went up. Now up and up move simultaneously is not allowed. So now my next rule says that 3 elements cannot keep going down consecutively. Which means that, see, from 3 to 2, we did go down. There was a move downwards. And then from 2 to 1 again, there's a move downwards. So 2 consecutive down is not allowed. Okay, so what's allowed then? See, intuitively, you'll get that 2 consecutive up or 2 consecutive down is not allowed, and 2 elements adjacent to each other cannot be same. So, which brings us to this intuition that signs must alternate. See, from 3 to 1 there was a decrease, so we went down. Now next should be an increase. So 1 to 2 is an increase, so a down move and then followed by a up move is allowed. And same here, from 2 to 3 there was up move, and from 3 to 1 there was downward move. So this is also allowed since signs are alternate. Now from 2 to 1 there's a downward move, and from 1 to 3 there's an upward move. So this is also allowed. From 1 to 3 we go up, and from 3 to 2 we go down. So up and down is also allowed. So these are allowed moves. Now forget about the question right now. See, let's say we are given, let's say we have an element 6 here in the sequence. Now, in order to determine what must go here, can we by 6 alone say what element must go here? We can just say that this element cannot be 6 by the rules, since 2 adjacent elements cannot be equal. But can we say that whether this number will be greater than 6 or it will be less than 6? No, we can't really. But let's say we have been given a move history as well. For example, when we came to 6, we went upwards. It means the move was up. So if we are given this, now my next move will be down, right? So to go down, there must be a decrease in number. So yeah, so that's why we have less than 6 here. Why not less than equal to? Because 2 adjacent elements cannot be equal. So what do we need? We need a direction history and we need the current value. Is that enough to tell what number will go next in the sequence? Yes, it's enough. So then we know that we are going to solve this using DP, since it says how many number of ways or how many valid arrays are possible. So we know that this is a dynamic programming question. Now we have this 1, 2 and 3. You remember 1, 2 and 3 were the possible values. Now my question says that you know, I want to find how many arrays, end at value 1. So that will be given by this. So now this says how many arrays end at 2 valid arrays, and this says how many arrays, valid arrays, end at 3. Now we have this up and down here. So this is a 2D array. We can also have, two 1D array as well. This is, so what we say here, like if our last, we cannot say anything just by value. We also need a direction history. So that's why we say, like if the last move was up and the current element is 1, how many number of valid arrays are there which end at 1 when the last move was up? So similarly, we can decode the meaning. For example, this will mean that number of valid arrays that end at 3 when the last move was down. So now let's see what happens. Let's see we are given this element 3, and let's say we are told that when we reach 3 we went upwards. So this was a move. So what could be the possible values here? If like the possible range of possible values, it is between 1 and 3. So can 3 be there? No, not really. Why? Two adjacent elements cannot be equal. Can 2 be there? Yes. So this can have 2. Can 1 be there? Yes, 1 can also be there. So the total number of possible values, 1 or 2 can be here. Correct? Now let's say that I take the case where 1 was present there. वैसे we had 2 cases, it could be either 1 or 2, but let's say it was 1 here. So now we know that this move was upward. So we kind of know that this move would be downward. And now we have to guess this. So how would we get this value? How do we get even this value? So dp of value, the number of valid arrays ending at 1, index 1, when the last move was down. So see, the last move is downwards. So this is how we'll get the value for this cell. Now we had 2 cases, remember? This could either have been 1 or 2. So let's say it was 2 here. And if we go upwards here, we know that alternate move will be downward here. So how many total arrays end at 6 when the last move was downwards? End at 2 when the last move was downwards. We'll get it via this. Okay. So now let's say these were the possible values, 1 or 2. So we could get this value by dp1 of down. So this is it. And dp2 of down. So if we add this, what happens? We get how many valid, arrays we can get, which ends with 3 when the last move was up. So this is how we derive the formula. So now we come to the key intuition part, which basically is, firstly, we are not counting arrays. Are we counting arrays? Not really. So we are just counting the ways. Remember this phrase, ways. And we want to calculate the number of ways at the end at each value, which end at each value, while remembering only one thing, which is the direction history. Since signs must alternate, that's all the direction history we need. Okay. Now can we optimize? Yes, we can. Let's say we need, this, there was an up move. Okay. And this is like y, element y. And we know there was an up move. So we'll know that there was a down move previously, correct? and there would be numbers here. So what numbers could be here? If there was up move, so these numbers can be less than y, correct? So for all possible numbers less than y and with a downward move, we, for all x less than y and a downward move, we'll do a summation. And when we do this sum, we'll get this value. Same for, down direction. So yeah, this is how we come up with the formula. Okay, now let's come to the code part. So here you can see that I have this mod variable, which is a final type, and you see we have underscores here, which basically is a readability feature in Java. Okay, now we calculate the total number of elements that are present in between left and right. So the reason I'm calculating this is, let's say my possible numbers are 1, 2, 3. So my left will be 1, right will be 3. So my size will be 3 if I calculate it using this formula. Okay, now let's say I had another possible value 0, 1, 2. So the number of valid arrays here will be equal to the number of valid arrays here. Since we're not actually seeing the actual values, we can just have that window starting 0. So it wouldn't matter. So this is one thing that we've done here. Now we've checked if n is 1. What is n? It's basically the length of array. Let's say I have just array of length 1. And I have, let's say, size possible values, 3 possible values. So how many valid arrays are possible? 3. So that's why we return the size. Okay, now coming to line number 13 and 14. I'll explain what is 16 and 17 later, but let's see what does line 13 and 14 do. So we basically create up and down arrays of the size 3. So now what we'll do is, we'll iterate up until the size of the array, and we'll, fill these arrays, fill these values here. So one thing to note here is that, let's say I am this was like for length 1, we simply return n, right? What if my array length was 2 and I had 3 possible values? So now I have to check. So let's say if my, now I'm checking for I equal to 0. Now I am checking that my 0 would be the last element, and my last move was up. So what's the total number of ways in which we can get this kind of array? So what are the possible values here? It's greater than 0, this move is up. So it will be less than 0, right? So how many values do we have which is less than 0 in here? 0 values. So simply we'll get 0. Now what happens if instead of 0, we had 1 here? Let's say we had 1 here. So what would go here? If the previous move was up, so any element less than 1 would go here. How many elements less than 1? Only 1 element. So that's why 1 here. And similarly 2 would go here. You can check. So we come to the formula that up of I equal to I. And then similarly we are going to, find it out for, like, if the previous move was downwards. Now what we are going to do is, let's say I have this. Now let's say my last element is 0 and my last move is downwards. So how many values are possible here? 2 values. How many values do we have greater than 0? 2 values. So 2 would go here, 1 would go here, and 0 would go here. You can calculate this. Pause and calculate. So this is how we get to the, this line 20 to 23. Okay, moving on. Okay, now we are at line number 25. Now, let's say we want to find the valid number of arrays of length n. So previously we calculated valid number of arrays up till length 2. Now we are going from length 3 up till length n here in line 25. Now what I'm going to do is I'm going to have a variable called running, and this will actually store something that I need to store in up and down arrays. Now, so when you up of I, so let's say this is up and this is down. So we've from this we are calculating a new array called new up, and from down we are calculating a new array called new down. Fine. Now here my first element would be running, which is like 0 initially. Then my running would be updated to down of I. So why down of I? Let's say I have like element 0 here, and this move is upwards. So whatever here we have, we know that we would have made a downward move here. So that's why from down of I, we are adding it to running, and then we are doing a mod, so that we can store that here. So similarly this will continue. Now again we we actually assign running as we assign 0 to running. Now what happens is we'll do the same for like this down array. Now let's say I have an array of like 3 elements, length 3. Now my last element is, let's say, 0, and the last move I made was downwards. Now this move will be upwards, right? So that's why we are taking it from up of I, and we are appending it to running. And every time we are doing a mod, since there can be an integer overflow, and then we every time we assign it to running, and then running's value is assigned to new down of I. Now we swap. What do we swap? We basically swap up and new up. Not necessarily up and new up, but we do assign new up to up, and we do assign new down to down, and down is new down. So we basically swap these values, and we continue up until length is less than or equal to n. And then what happens? We store the result. So my result would simply be summation of up of I and down of I, with any element like 0, 1 up till size could be the last element. So that's why we do summation and a mod here because of integer overflow, and the question asks us, and we return the result in integer format at the end. So this is how it goes. And yeah, so what happens with time complexity and space complexity? So you remember there's this n, which is like the length of array, and then this is size, which is like the number of elements allowed. So this will be time complexity of big O of n into size, and space complexity is big O of size, since we are having dynamic program and storage there. So yeah, that's why. I hope I was able to explain the question. Thank you. Bye.